Okay, great. Yeah, so let me just start by giving a sort of quick recap of what we talked about yesterday. So the whole lecture series is about the integral Hodge conjecture, which is this statement here, namely that any Hodge class or integral Hodge class. So remember that this notation here is for HRR C. Sorry, intersection. It's the integral cohomology. So the statement is that all such classes are in fact algebraic. And we saw one proof yesterday that, well, that was sort of the first technique to prove that a class was not algebraic, and it used a specialization argument. So today I will try to say more about the, well, historically first counterexample, which was due to Attia and Hirzebruch in the 60s. I'll sketch this the proof of this result here, namely that there's a smooth projective sevenfold with a non-algebraic torsion class. And the example and especially the technique is quite different from what we saw yesterday, in particular because it concerns a torsion class. So the class we had yesterday was not torsion. But yeah, maybe before we go there, let me again emphasize this thing here that that the integral Hodge conjecture is an interesting statement for curve classes. So we had these where are these groups? Yeah, these quotients here. So this was a finite group that measured the sort of the failure of the integral Hodge conjecture, and in the particular case where this was a curve for codimension n-1, this was a birational invariant. So that means that even for threefolds, this is sort of an interesting question. It's not clear that all codimension 2, degree 4 classes come from codimension 2 subvarieties. So maybe before we start, let me just survey a little bit what's known in dimension 3. Yeah. All right. So for threefolds, we only have sort of 2 codimensions the question is basically about codimension 2 cycles. We know that for codimension 1, it's true that all 1-1 integral Hodge classes are algebraic. So the question is about curve classes. And we saw one example where we had a threefold where this quotient group here was non-trivial. So this was this hypersurface of degree 125, where there was a class which was not algebraic but had some algebraic multiple. So 125 times that class was algebraic. Of course, 125 is a very large number. So one could ask, well, this is a threefold of general type, and is this? I mean, these counterexamples, do they sort of only appear for general type threefolds? After all, we saw that there was some connections between these groups here and birational invariants. So maybe it just turns out that they're just 0 for all threefolds of low Kodaira dimension. And in fact, there are statements in that direction. So the main positive result is for union ruled threefolds. This was proved by Claire Voisin, she proved that the integral Hodge conjecture does hold for all uniruled threefolds. So on a uniruled threefold, any degree 4 Hodge class is in fact algebraic. So you can't find, Collar type counterexamples here. And yeah, maybe it's a little bit. I mean, it's a big class of threefolds even. So if you wanted to use this as a sort of birational invariant, it says that it wouldn't be possible for threefolds at least. Okay, and she also proved something for Codard dimension 0. So the integral Hodge conjecture holds for threefolds with Codard trivial canonical bundle and also vanishing H2. And this was extended by Totaro, who proved that it actually holds for all Codard dimension 0, as long as you have a section of the canonical bundle. Yeah, so in particular, it holds for all abelian threefolds, which is not at all obvious. Yeah. Okay, so in light of that, one could ask, does it hold for all threefolds with Codard dimension 0? And in fact, the answer is no. So it really stops at Codard dimension 0. You can actually find counterexamples to the integral Hodge conjecture for threefolds with torsion canonical bundle. So again, just to sort of remind you that for surfaces, there are sort of 3 types of Codard dimension 0. So we have K3, we have abelian, and then we have Enrique surfaces. And in fact, Enrique surfaces, those are that's where the sort of counterexamples appear. So here's the next result, which I don't think I'll prove, but I'll mention it anyway. So it's with Olivier Benoit. And the statement is the integral Hodge conjecture can fail even on very simple varieties. So you take an Enrique surface S times an elliptic curve. So even for that product, the integral Hodge conjecture fails. So of course here the Codard dimension is 0, being a product of Codard dimension 0 varieties. And in fact, you have no section of the canonical bundle. Which says that that above result by Totaro, this is like really sharp. I mean, you couldn't remove any of these hypotheses. Yeah, so to me, this was a little bit surprising, at least. This is a very simple variety, and yeah, even there you have non-algebraic classes. So let me maybe make a remark: which classes are non-algebraic on this product here? Because here there are not that many interesting classes. So, well, by the Kunev formula, we know exactly what the H4 is. Well, we have one part coming from H4 of the surface times H0 of the elliptic curve, and everything here is algebraic because we can represent it by a point times the class of E. The same thing goes for H2 tensor H2. So here you can just take a divisor on S times a point on E. So everything here is also algebraic, although they're represented by very concrete subvarieties. But there's this like middle piece here, which is a little bit more subtle. So here there are classes. So because this is an Enrique surface, well, this here would be H1 of SZ. So we know that this is Z mod 2. So there's a torsion class here, and then we tensor it with H1 of the elliptic curve. So there are some torsion classes in H4. And here it's not so clear whether they're algebraic or not, because, you know, okay, then, I mean, certainly, yeah, I mean, you're not taking the product of two algebraic classes here. We're taking classes of degree 3 and degree 1. So, yeah, it's really not clear whether this like tensor product would be algebraic. And in fact, it turns out not to be the case. And the proof really uses a degeneration argument like we saw yesterday, but it's a little bit different. So to just say a little bit about the proof. So so here we take this class alpha in H1 with CMOD 2 coefficients. So we use the fact that every Enriquez surface is a quotient of an K3 cover of a K3 surface. So it has this like special class alpha, which represents this double cover. So at least we can, well, think about this class somehow geometrically. And you can compute using essentially by analyzing this decomposition here. You can see that the integral Hodge conjecture holds on this product if and only if this condition here holds. So for every class on E, in H1 of E, there should be some correspondence or cycle on this product that induces this from this class alpha. So every class in H1 of E should be obtained from alpha via some algebraic correspondence. Okay, so this is just basically a topological computation, but it translates this integral Hodge conjecture into something that's into a statement that one could hope to sort of falsify. And then from there,
I have a question.
Oh yeah, thanks.
About this Z, what should be the quantifier next to it? Is it exist or for all?
Oh yeah, it exists indeed. Yeah, thanks.
Okay, thank you.
Right, yeah, so okay, so the integral Hodge conjecture holds if and only if there exists some cycle that induces beta for n, yeah, via this alpha class. Okay, and then basically what we do is another degeneration argument. You sort of assume that this condition holds for any genus 1 curve, and then you write down a family of elliptic curves that degenerates into a nodal thing, a nodal rational curve, and then you get a contradiction on the special phi. So again, the proof is, I mean, uses a sort of degeneration argument. I don't think I'll say more about the proof at this point. Let me just say that I'll add the details to the notes. So if you're super curious, you can look them up yourself. But it's a little bit more involved than the result from yesterday with the Collar's result. So I think I'll focus on the result by Tia and Hiftbrook today, and you can read about this yourself if you want.
Can I ask you something?
Yep.
But why does the assumption of Totaro make, I mean, is not compatible with this example? The assumption that the canonical bundle has sections?
So in this example, there's
What is the reason why this example, I mean, yeah.
Yeah, that's a very good question. I mean, it's, this is a little bit mysterious. I mean, there's certain estimates. Yeah, I mean, in order to explain that, I think you really need to see the proof. Basically, the way these proofs work is that you have your threefold, and you take. Let me try to draw. So you have some threefold, and basically what you do is to take hyperplane sections H of a very high degree, and these hyperplane sections, they move in big families. So you can think of X as embedded into a big projective space, and then S is obtained, a hyperplane section. And then you look at classes coming from the push forward to X. And what they show is that basically you can reach any class here from the H2 of some surface here. And basically what you need to show is that you have enough variation of Hodge structure here that you can actually represent all classes from something that's algebraic on the surface. And this variation of Hodge structure argument, it just sort of works well with this assumption here. But it's a little bit subtle. It's hard to pinpoint exactly where it's used, but yeah, I don't know. It's I guess Hodge theory is the answer. Yeah. Okay, so let me, instead of doing that, let me give you one more example of this sort of specialization technique. So this will be a threefold of Codar dimension 1. But it will be a proof that's a little bit more similar to Collar's technique. And I had a question yesterday about which fields you can apply this specialization technique to. So there was this Hilbert scheme argument, and we needed, uncountable fields for that to work. But in this example, we can see that this actually works for with examples over Q or a Q bar, or so this is an example where we specialize over a countable field even. Okay, so what's the statement? Okay, so this is what we're going to prove. This is an example due to Hassett and Chinko, and also Totaro. So he was the one who remarked this thing about rational numbers or examples over Q. So so let X be a very general 2-3 divisor. Then every curve has even degree over P1. Okay, so that's sort of the original statement of Hassett and Chinko. And then Totaro said that, well, this very general assumption is not really needed. There's Zariski open sets of hypersurfaces over Q where this also works. Okay, so the geometry here is it's interesting. So it's a 3-4 hypersurface, which means that, well, if you view this as a family of surfaces over P1 via the first projection, the fibers here are K3 surfaces. So it's a K3 fibration. And the statement is that, well, if I take any curve on X and look at the projection to P1, then the degree is even. And that gives us a counterexample to the integral Hodge conjecture, because we know the topology of these things. So the H2 is just given by the H2 of the, well, P1 cross P3. And the H4 is, well, it's the same, given by something that pushes forward to, fibers on, well, P1 and P3. So we know what the classes look like and how they intersect. But here, certainly in H4, you do have a class that sort of looks like it should be, which has even, odd degree on over P1. So this class here has degree 1 over P1. So that class couldn't possibly be algebraic. Yeah. So yeah, it's a little bit similar to Collar's result. He also used the Lefschetz hyperplane theorem to get a description of the H4, and somehow what we're saying is that we have a counterexample because we know something about the degrees of all curves on X. Okay, is there any questions about the statement here? Okay, yeah, so this is by Hassett, Chinkel, and Totaro, and basically this example is taken from the paper on the integral Hodge and Tate conjectures over a number field. Okay, so let's follow, the same strategy from yesterday. We want to prove that a statement for general hypersurfaces in here, but we can prove the statement by specializing to a singular hypersurface. So the hypersurface we're going to use is this one. It's special because it has, well, few monomials, and yeah, it's certainly defined over Q. And the claim is that every curve on that threefold has even degree over P1. Okay, so yeah, that's this is a kind of remarkable equation. Yeah, somehow it's simple, but just complicated enough so that we get this statement that we need. Okay, so now comes the characteristic P, or sorry, the specialization to characteristic P thing I mentioned. So we can view this as as something that's defined over Q or Q bar. So basically, well, we can look at the Chow group of 1 cycles over Q bar, and there's a specialization map to while taking mod P. Yeah, and the thing is that it's enough. So this is compatible with the intersection products. So if we want to show that everything here has even degree over P1, then it's enough to show it over here. So every curve on here has even degree over P1. Yeah, and okay, so the setup is as follows. We take a curve in X, and we want to basically show that the intersection number with a fiber, or we want to show that, well, we take a point here and we want to show that the number of pre-images is even. So to prove that, we basically just need to restrict to the generic point of P1, and this is given by some field extensions, and we're looking at the degree of that field extension. So we can base change to the generic point of this P1. And we can even restrict further to, well, not just to the generic point, but even the field of Laurent series around this point here. So now we're basically completing here, and then if we can show that the degree over that field is even, then we're done. Okay. Okay. So here's the claim. We have our equation, or at least the affine equation, and we need to show that this equation here has no rational solution over any odd degree extension of this field here. Yeah, so if we can show that, then we're done. Then any curve has odd degree over even degree over P1. So there cannot be any odd degree extension over this field where you have a solution. Okay, so now I really like this argument. I mean, we're basically finished, but yeah. So assuming that such a solution exists, so I mean, remember, we're computing over this field. So it means that there's a solution of that equation in this field. So there are Laurent series in some parameter S here. And the fact that this is odd degree over this field means that this valuation is an odd number. Okay, so we have solutions T of S, x0 of S, x3 of S, so that when you plug in these power series to this equation here, we get identically 0. Okay, but this is impossible. So if we try to do this, so we plug in x0 here, x1 here, x3 there, then now comes the whole point of this, of choosing this equation. If we look at the valuation in, oh, sorry, this should be, yeah, oh, this is right. So here, we would have a fourth power of, a power series in S. Here we would have t times the fourth power. And here we would have t squared times the fourth power. So if we take the valuations in S modulo 4, we would get 0 r, just coming from this, 2r coming from t squared, and 3r coming from t cubed. Yeah, and yeah, so the thing is that if r is odd, then these numbers here are different modulo 4. So it means that if you have a solution of this equation in power series, it means that they have to sort of all be simultaneously 0. But that gives that x0 equals x1 equals x2 x3. They're all 0. But that's not possible because this is not a point in projective space. Yeah, so at the end here, there's a sort of very clever valuation argument that really uses this specific form of the equation to get a contradiction. And of course, this is nice because it means that we can get examples over Q bar. Basically take anything that specializes to the above equation modulo P, take anything of this form, then for that hypersurface over Q bar, we have a counterexample. All right, any questions about this? So again, if this was a little bit fast, then I'll definitely put out the notes on my webpage for all of these talks. So you can go back and see the argument in more detail if you would like. Okay. Okay, I think I'll move on then to sort of the main result of today. So, okay. Now I'm going to sort of completely reboot the lecture. So if you fell asleep during that proof, you can resume, and now comes something completely different. Yeah, this is going to be about the famous result of Attia and Hitzebrook from the 60s, and we're going to see a new counterexample to the integral Hodge conjecture, but the argument is now completely different. It doesn't use degenerations or specialization arguments. Okay, so what we're going to do is to look at topological obstructions. So of course, the sort of overlying question here is, well, given a cohomology class, how do you prove that it's not algebraic? So of course, there's one obstruction coming from, well, complex geometry, saying that, well, this must at least be a type PP, so it must be in the middle of the Hodge. But this, of course, is not so interesting. So, but Ottem Hitzebruch discovered a sort of much more subtle obstruction, and it's the following. So if we have a class in integral cohomology, if this is algebraic, then all of the odd Stanrod operations have to vanish. I'll say what Stanrod operations are in a second, but basically they're topological, cohomology operations. That's defined sort of for all topological spaces, and it's sort of a miracle that if this class is algebraic, then these cohomology operations are 0 for all odd I. Okay, so this is, so I don't, I'll explain what this means in a second, but right now it's just sort of a clear topological obstruction for being algebraic. Okay, so what are Stanrod operations? Well, so SQ it's a cohomology operation with Z-mod 2 coefficients. So it means that it's a map from Z-mod 2 cohomology to Z-mod 2 cohomology, but it shifts the degree by I. Okay, so there's a few ways to define these. I won't go into the definition. I'll just list the sort of properties that we need to understand the proof of this result. So the first is that the 0th Stanrod operation is the identity. So here it's the map from HM to HM, and it does nothing on a cohomology group. And if I take a class in HM and I apply SQM, then this should just be the usual squaring operation. So these are sometimes called the Stanrod squares for this reason. So you should think of these as sort of generalized power operations inside cohomology. Okay, so the SQM is the square, and all of the higher SQs are 0. Okay, yeah, and we also have the sort of total Stanrod operation, which is sort of the, well, you take the sum of all of them, and this satisfies Cartan's formula. That if I take the product of two classes and take the total SQ, then it's just the product of the SQs. Or if you want, we can compute Stanrod operations of products just from the Cartan formula, which is this thing. Actually, this is what we're going to be needing in the proof. This is basically all we need. Yeah, of course, like all cohomology operations, this is required to be functorial. So if you have a map between X and Y, this is supposed to commute with pullbacks in cohomology. All right, any questions about Stanrod operations?
I have a question.
Yep.
What is origin of this operation?
Oh, it comes from, I mean, it's a long story going back to, well, Stenrod, and I think basically it was René Thom who really used Stenrod operations actively in problems in topology and differential topology in the 50s. I don't know what's the origin. There was a pretty big development, I guess, in the 40s and 50s in algebraic topology, where Stenrod, Thom, Sarah, I mean, many people investigated these operations and applied them to sort of concrete problems in topology. I mean, there are many relations to, I don't know, like Chern classes and Stiefel-Whitney class, stuff like that. So yeah, I don't know, if you haven't seen this before, I definitely recommend Milner's book, Characteristic Classes, where this is explained. I mean, it's a really long story, but it's very interesting one. So yeah, I recommend. Okay. Yeah, so for us, what another property that will be important is the Wu formula. So if we have a smooth map between x and y, y and x, then we know exactly how to compute the skew of the push forward of a class, and it's just given by the push forward of the skew of alpha times Stiefel-Whitney class of the normal bound. So here the normal bound is a virtual vector bound. So it's the difference between the tangent bound of x and the tangent bound of y. And the Stiefel-Whitney class is defined by like this, and then everything here takes place in Z mod 2 cohomology. Okay, right, and yeah, so the whole point now is that if y is a complex subvariety, then while the fundamental class is just the push forward of one via, taking a desingularization of the inclusion, and the thing is that for closed complex subvarieties, then this normal bound here, or the Stiefel-Whitney classes, they're just the mod 2 reductions of the Chern classes of the normal bound. In particular, everything is 0 for the odd degree Stiefel-Whitney classes. So we only sort of get even. So if we try to look at this contribution here, we only get terms that have even degree, no terms in odd degree. And here we're really using the fact that this is a complex subvariety, because we're relating the Stiefel-Whitney class to the Chern class of this vector bound here. So here we're using that this is a complex vector bound. Okay, so what does that give? Well, it means that the Stenrod operation on the class that we're interested in. So then, I mean, by this Wu formula, this is just it's this Stenrod operation of this push forward, and by Wu's formula, this is the push forward of this element here. But the thing is now, I mean, we said that this class has only terms of even degree, And so we have our result. All of these odd standard operations, they vanish on the mod 2 reduction of y. Yeah, okay, so now we've proven this obstruction due to Ottem-Hirzebruch, saying that all of the odd standard operations have to vanish for such a class. Yeah, any questions about that? Okay. Well, what we need to do now is to actually find an example where that happens. I mean, a priori, it just could be that it's just true, and yeah, well, it could be true for all integral Hodge classes. So we need to actually construct a variety and a subvariety or a class where some odd standard operation is non-zero. Okay, so now we get back to sort of this problem of constructing varieties with interesting properties. So in this case, we want a variety which well have which has some like strange cohomology ring, and one can construct those using quotients. So if we take a finite group, well, we have a classifying space of principal G bundles. It's called BG. And one way to define it is just, well, take any contractible space where G acts freely, and then look at this quotient here. And this is well defined up to homotopy. And it's a sort of, yeah, the cohomology of this space here is just given by the group cohomology of this group G. So just a few examples. So B of Z. So if Z is the group, then we get the circle, and the space that Z acts on is just R with translation. If we take Zn, we get just a product of S1s, and we can act on Rn using a similar translation. So B of Z2 is Rp infinity, and here we let Z2 act on the infinite dimensional sphere, and B of C star is the complex projective space. Yeah, so typically, even for very simple groups, these spaces here are not algebraic varieties. They tend to be sort of infinite dimensional. Okay, so the group that was used by Ottem-Hirzebruch was the product of three well, copies of Z mod 2. In that case, well, we know how to compute the cohomology. It's just given by the cohomology of Rp infinity, which is Z mod 2 in a polynomial ring. And if I take three copies of Z mod 2, then there's a Kunneth formula that basically gives you a formula for the cohomology group here. And it's just, so we get a polynomial ring in three variables over F2. Okay, so at least here, this is a cohomology group, or sorry, cohomology ring, which has a lot of torsion in it. And we could try to hope, or we could hope to find some elements here where the standard operation is non-trivial. And in fact, that's exactly what happens. So if we take the product of x1 times x2 times x3, and just compute this element here as SQ3 of this. If we use the Cartan formula and just sort of brutally compute everything here using that, well, we see that this element here just expands out and like this. So I'm just using the Cartan formula. And yeah, if you just do the algebra and actually compute all of the terms here, we see that actually this element here is non-zero in yeah. So this here is certainly non-zero inside this polynomial ring. Okay, so I'm not going to bore you with the details of that computation, but it's something that's it's just algebra. Yeah, but then once we have that, we can just define alpha to be the Bockstein element of x1 times x2 times x3. So remember that the Bockstein homomorphism is the one that you get from this exact sequence. So so we have a class in H3 of Z-mod 2. So by the long exact sequence, the Bockstein element is the corresponding class in H4. Okay, so that is the class which now lives in H4. And this satisfies exactly the condition we want, namely that the third standard square is non-zero. Okay, the details are not that important. You know, here we find some group that gives us a class which has the required property that the standard square is non-zero. The real problem here is that this BG is not a smooth projective variety. It's infinite dimensional even. So even if we found some topological space where this is where this is non-zero, then we still need an example in algebraic geometry. Okay, so for that we use a very useful construction. It's known as the Godot-Serre construction. So it's the following. So if we take a finite group, for instance, the product of 3 Z-mod 2s, well, Serre showed that given any integer r, we can find a representation of G on some very big projective space and a smooth invariant complete intersection inside this projective space, so that G acts freely on this complete intersection and the dimension of Y is equal to R. So R is any chosen number. Okay, so that's easy, but then also this quotient here is, well, because G acts freely, this will be a smooth projective variety. And this will have sort of the interesting property that the group cohomology here embeds into the cohomology of X. So the quotient of this complete intersection contains interesting cohomology groups up to the dimension here. Okay, so basically what we're doing here is approximating this BG by some projective variety. So it's not true that they're homotopy equivalent, but at least their cohomology groups are related up to dimension R. Okay, so that's one very useful way to construct varieties. We can just take quotients of complete intersections, and those will typically have some of these properties. But now we're basically done. Like now the proof is finished. So we just constructed a class in H4, which had the property that this third standard square is non-zero. So this element here lives in H7 of GZ. So if we just apply this the Serre construction here with R equal to 7, then basically we construct some variety where this where the cohomology group here contains everything that we want. So in particular, it contains this class alpha, and we know that the square has to be 0 because this is an injective map. Okay, so then we finally get that X admits a non-algebraic class in H4. Yeah, that's the end of the proof. And if you analyze this explicitly, we can see that actually we can choose the canonical bound to be a torsion in this example. So this is codimension 0. Okay, let me just sort of try to summarize a little bit what we've done. So we started with this observation that if we have an algebraic class, then if we have something that's the fundamental class of a variety, then all of the standard squares have to be 0 for that class, and that's because this Stiefel-Whitney class had only terms of even degree. Okay, so this was basically just topology. And then we've constructed some space, infinite dimensional space, where we had a class satisfying SQ3 being non-zero. And then finally, we've constructed a variety X, which was a quotient of a complete intersection, so that complete intersection, this quotient here contained the cohomology of our infinite dimensional space up to some degree, and that's enough to produce a counterexample. Yeah, so this is a very useful technique if you want to produce strange examples. Look at quotients of complete intersections. They have sort of interesting cohomology in them. Okay, I think I'll probably end here a little bit early. So yeah, thanks.